point, because we have already completed one iteration, it is post 3. Post 3 is true here, and it's true. Oh, by the time we get here, post 3 is still true. Now, we have a little bit of a problem, don't we? You can see that the precondition depends on some mumbo-jumbo, but as a part of its components, post 3 is also a part of it. We have a little bit of a circular thing going. But do you expect a circular thing going when we're dealing with loops? Yeah. Obviously. Okay. What about post 3? What about post 3? Well, we go through step 1, 2, 3, 4. Okay, so we say step 1. Okay, I'm just going to simplify that. The right-hand side refers to the left-hand side. We go to step 2. Okay, let me see what step 2 does. Step 2 says, call the right-hand side a function, and then step 3 tries to find the inverse of that. So step 2, we'll just say, f of x is x plus 1, which is the right-hand side of the assignment statement. Step 3, we'll try to find the inverse function. So the inverse function is f prime of x, which is x minus 1. Okay, are there any questions at this point? Okay, so we are just reapplying everything that we know about this sort of assignment statements. Okay, which means this is good. We go to step 4. We will apply the substitution operation. So that means if we are just doing it very mechanically, we'll just say that post 3 is the result of a substitution operation performed on pre 3. We are locating all the occurrences of x and replacing each and every occurrence of x with f prime of x. Is that making any sense? Well, how do I get to step 4? How do I get to here? I'm just blindly following step 1, 2, 3, and 4. Does it have anything to do with statement 3 or line 3 is in the loop? No. It doesn't matter at all. This has steps 1, 2, 3, and 4 can be derived like that simply because line 3 is a self-referencing assignment statement, and the function on the right-hand side is reversible. That's all. Yep.
Okay. Why are we using the inverse function?
That is something that we have already established, like when we talk about a self-referencing assignment statement. The inverse function's purpose is to reverse the operation so that whatever relationship was true before can still be true, but after this little modification. It is the undo. Okay, the f prime is the undo. It's basically saying if I can undo what line 3 did to x, then whatever I knew about x, how it relates to everything else, will still be true at this point. Okay, so we just go ahead and blindly apply this. Oh, but we can't, can we? Because pre 3 mentions something about post 3. So if I can do this, that's no problem. I can expand pre 3 and just copy and paste it here. Okay, I don't have a problem with this step at all, except I'm stuck now. Because what I'm trying to solve here, which is post 3, is a part of this equation as well. Are you guys seeing the problem here? It's kind of like saying I have one unknown, which is post 3 here, and in order to compute or derive the unknown, I have this long expression that also involves the unknown. Unfortunately, unlike in algebra, we cannot apply the algebraic operations to try to resolve what post 3 is. Okay, that looks kind of mysterious, but we'll just let post 3 sit like that for the time being. We'll deal with post 4 instead. Okay, we'll just kind of jump around and say, okay, we'll leave that one alone and derive what is post 4. How many ways do we get to post 4? There are 2 ways. Okay, in theory there are 2 ways because there's one way to say that we go here and then this condition is false and then we go straight to post 4. The other way is to say that we go through at least one iteration, go back to this point, the condition is false, and then we exit to post 4. So when you look at post 4, the first thing we know is x is less than 3 has to be false, because otherwise we would not be exiting the loop. Is that making any sense? And there are two ways to get there. First, x equals to 0, we get this here because, if we go from here, I know it cannot, because x cannot be 0 and not be less than 3 at the same time, but it will all work out. Trust me, it will all work out. Or post 3, right? Because if I go through at least one iteration, then post 3 is true here. Post 3, post 3, post 3, post 3, post 3, post 3, post 3. This condition is false. And then post 3, post 3, post 3, post 3, post 3, post 3, post 3. Okay? So that's why, I write post 4 as not x is less than 3, because there's no way I can get there unless x is less than 3 is false. But on the other hand, we have two ways to merge the paths to get to that point. Okay? Do you see post 3 everywhere? That means, post 3 is a condition that it seems to be always true. I mean, it's everywhere. Why do I say it's everywhere? Look at pre-3. Pre-3 mentions post 3. Post 3 itself mentions itself, and the post condition, post 4, also mentions post 3. Okay? And that's why post 3 has a special name. Post 3 is called a loop invariant. Okay? What do you think the word invariant means? Vary means to change.
It doesn't change.
It does not change. It is a constant. It is a condition that is always there. Okay? And that is the core of this whole discussion. What exactly is post 3? Okay? The derivation or coming up with the loop invariant is way beyond the scope of this class. So I'm not going to say why I suspect the loop invariant is blah. What I will do is to say, well, if someone tells me and say, Tag, you might want to consider a possibility. Maybe the loop invariant is blah, blah, blah. Well, I should still be able to put it in and verify that the loop invariant will make everything else work out, right? So that's exactly what we're going to do in the next 5 minutes. I guarantee 5 minutes is all that we need to get this done. So we'll say we suspect that post 3 is x is less than or equal to 3. Okay? It's just a hunch. Somebody told me, whatever. Okay? But can we verify this? Can we verify this is right? Okay, just because someone tells me it can be the answer doesn't mean that it is the answer. Okay, so the first thing we'll do is we'll plug it into pre-3. So we'll take this whole expression here, paste it here, and then we'll say since we suspect post 3 is this, then we'll say x is less than 3 and x equals 0, or x is less than or equal to 3. All right, that's a mess. Can we simplify this a little bit? Well, we'll look at the disjunction first. When I say x equals to 0 or x is less than or equal to 3, can I simplify this equation? I mean, can I simplify that?
Just say x is equal to 3.
It simplifies to that, right? Because when you are looking at a disjunction, you're taking the union of the two sets. Okay? One set has a single data point. The other one is bigger, including that one single data point. So when you take the union, you're basically just taking the bigger one. Describing x is less than or equal to 3 is a more general description. In a disjunction, you just take the more general description. Yep.
Back to the loop invariant. Why do they call it a loop invariant? Invariant means it does not change.
It does not change. The condition is always true.
So you're not referring to variable that change. You said the condition does not change.
This condition does not change. Once you enter the loop, it is always there. Now this one can be simplified, because when I say x is less than 3 and x is less than or equal to 3, guess what? We take the more restrictive one. Because in this case, this is a smaller set compared to this one. This one is completely inside the other one. When you're taking a conjunction, you're trying to restrict it, right? So if you have a subset, if one is a subset of the other one, you just take the subset. So in this case, the subset is to say that x is less than 3. All right, so pre-3 is okay, but we don't know whether it's working out or not. because we don't know until we perform this step here. So we'll just work out this step here, which is not hard. I mean, it's once we know pre-3 is simple, like this, then the substitution operation is fairly easy to carry out. And f prime of x is x minus 1. So after you do the substitution operation, it becomes x minus 1 is less than 3. And if I know that x is an integer, this is the same as saying x is less than or equal to 3. Is everyone convinced that if I guarantee that x has to be an integer, saying that x minus 1 is less than 3 is the same as saying x is less than or equal to 3? Is that okay? Hey, that seems to be working out, because the suspicion that post 3 is this does work out. Okay, so this is a verification already. And we have 2 minutes left. We'll derive post 4. Once we get past post 3, everything else is actually not too bad. Okay, so we'll simplify this, to be x is greater than or equal to 3, x is equal to 0, or x is less than or equal to 3. And we'll do the simplification inside the disjunction first. How do you think I should simplify this disjunction? Is one a subset of the other one? This is the superset, this is the subset. And because we are taking a disjunction, we take the superset, the bigger one. So the disjunction simplifies to x is less than or equal to 3. Now we're looking at, this number, this set of number does not completely include the other one, and vice versa. These two intersect. Okay? They intersect only at one single point. What is that?
3.
X equals to 0. Right? So now we have the whole thing worked out. Just because someone gave me a suggestion and say, Tech, why don't you think, maybe x is less than or equal to 3? Now, the reason why that person gave me this suggestion, that is beyond the scope of this class. Okay, coming up with a loop invariant is difficult. Okay, so you guys don't have to worry about why a loop invariant is the loop invariant, but you should be able to work this out and verify that the loop invariant does make everything else work out.
When are we going to have our next class?
Working on it. So I think it will be a pre and post condition thing, and I'll probably work on it like in my office right after the class.
Did you take roll earlier?
No, I did not take roll today, so you're fine. Everybody's fine. Yep.
That's a get a paper somewhere.
Sorry?
I have to get a paper somewhere. Do you not know that how it goes? For computer science? Is that a different department?